Hi, so in my last video, I taught you how to calculate equilibrium constants from concentrations. If you haven't already watched that video, be sure to do that first so you can learn about how to make an ice table. In this video, you're going to learn how to calculate equilibrium concentrations from initial concentrations and an equilibrium constant, a harder process that will require you to dust off your algebra skills. Are you ready? Let's go. So once again, as with many things, this is a multi-step process. So first I'm going to walk you through the steps, and then we're going to apply them to some problems, starting with a fairly easy problem and then working our way up to a rather complicated one. The first step is to make an ice table as I showed you in the last video, showing all reactants and products. You're going to fill in the known concentrations just like we did before. Now in these sorts of problems, we don't have any equilibrium concentrations given, and so we can't calculate concentration changes with a simple addition or subtraction like we did in that other video. What we're going to do instead is use algebra. We're going to use x to represent one of the concentration changes, and then we're going to solve for the other changes in concentrations in terms of x. Next, we'll calculate the equilibrium concentrations in terms of x. And then when we've done that, we can use our ice table to write the expression for the equilibrium constant in terms of x. We'll reorganize that expression so it's in the form of a quadratic equation. ax squared plus bx plus c equals 0. And then we can use the solution to the quadratic equation to solve for x. Finally, we're going to take that value of x, put it back in our ice table, and use that to get actual numbers for equilibrium concentrations. Now I realize this process doesn't make a lot of sense just by looking at the steps, so let's actually apply it to a problem. Here's a problem in which nickel oxide is being treated with carbon monoxide gas, and that is going to form solid nickel and carbon dioxide. We're given the equilibrium constant at 1500 Kelvin. Now, keep in mind equilibrium constants do vary with temperature, so it is important that we know the equilibrium constant at the particular temperature that we're working at. So we're starting with a mixture of solid nickel oxide and 0.45 molar carbon monoxide, and we want to know what the equilibrium concentration of CO2 is. Let's start by talking about the equilibrium constant for this reaction. We always start out by putting our concentrations of our products in the numerator of the fraction. Here our products are solid nickel metal and carbon dioxide, but we don't include anything whose concentration doesn't change in our equilibrium constants. So that includes all solids. Therefore, we don't get to include our concentration of nickel metal in our equilibrium constant. And if you look over at our reactants, we also have a solid, so our equilibrium constant is actually just going to look like this. Just the concentration of CO2 divided by the concentration of carbon monoxide. So when we make our ice table, we just need to look at those two. We don't care about the other concentrations because they are constant. So let's go ahead and fill the known concentrations into our ice table. According to our problem, we're starting with 0.45 molar carbon monoxide. Do we know the other initial concentration? Yes. We're starting with no carbon dioxide, and so that's going to be 0. Now let's move on to step 2, where we use x to represent one concentration change. We need to pick one concentration, and I'm going to pick carbon dioxide. Right now we have no carbon dioxide, so the only thing that can happen is that we make some. I'm going to say the amount we're going to make is x. That's our change. Then our equilibrium constant will be 0 plus x, which equals x. For step 3, we're going to use stoichiometric ratios to solve for other concentrations in terms of x. Our balanced equation tells us that for every mole of carbon monoxide we consume, every mole that gets used up in this reaction, we make 1 mole of carbon dioxide. We're creating x molar carbon dioxide, therefore we must be consuming x molar carbon monoxide. So for change, I'm going to write minus x here because carbon monoxide is going away. And now, of course, we can use that to calculate the equilibrium concentration for carbon monoxide. We had 0.45, we subtracted x, therefore we end up with 0.45 minus x at equilibrium. Step 4 is to write the expression for our equilibrium constant in terms of K. We already wrote the expression for our equilibrium constant earlier. It's the concentration of carbon dioxide divided by the concentration of carbon monoxide. So now we can take the values from the table and plug them into that. X for carbon dioxide and 0.45 minus x for carbon monoxide. And we'll set that equal to the equilibrium constant value that we had in our original problem, which is 4.0 times 10 to the third. So here we have the algebraic expression, and we need to reorganize it so it's in the form ax squared plus bx plus c equals 0. So the first thing we're going to do is we're going to multiply both sides by 0.45 minus x. That gives us the following. X equals 4.0 times 10 to the third times 0.45 minus x. Now let's take that constant and distribute it through the parentheses. So x 1,800 minus 4,000x. Now we need to get everything on one side of the equation so that's equal to 0. So we're going to add 4,000x to both sides and subtract 1,800 from both sides. And we end up with 4,001x minus 1,800 equals 0. So in step 6, we're supposed to use the quadratic equation to solve for x, but we don't actually have a quadratic equation here. We only have an expression in terms of x and a constant. There's no x squared. So we actually don't need to use the quadratic equation. We can just go ahead and solve this for x, and when we do, we get x equals 0.45. Now in step 7, we'll take our knowledge that x equals 0.45, and we're going to use that to solve for equilibrium concentrations. So here's our original ice table, and then we're going to plug in this value of 0.45 anywhere we see x. So let's look at carbon monoxide first. Equilibrium concentration is 0.45 minus 0.45, so that means 0. There will be nothing left at the end of the reaction. Now let's look at carbon dioxide. The equilibrium concentration was plus x, so that's 0.45 molar. So let's think about our answer and whether or not it makes sense. Our equilibrium constant for this chemical reaction was 4.0 times 10 to the third, which is a pretty large value. Now remember, when we see a large value for the equilibrium constant, we normally think of a reaction that favors products. So we should have more products than reactants at equilibrium. And in fact, when we look at our equilibrium concentrations, we see that there are considerably more products than reactants. So our answer does make sense. Now, this is a very simple example. It's particularly easy because we only had to do very simple algebra solving for x. But most equilibrium problems aren't like that. So here's a more difficult problem. This is a reaction in which we have carbon monoxide reacting with water in the gaseous state to give carbon dioxide and hydrogen gas. We have a reaction mixture of 0.250 molar carbon monoxide and 0.200 molar water, and we want to know what the equilibrium concentration of all the reactants and products will be. So we're going to start out by making our ice table showing all the reactants and the products, and then we're going to put in the known concentrations. So here are the reactants on the left, carbon monoxide and water, and here are the products on the right, carbon dioxide and hydrogen gas. Notice that I abbreviated the table, so now we're just down to ice for initial change and equilibrium. Let's fill in our concentrations. So the reaction mixture initially contains 0.250 molar carbon monoxide and 0.200 molar water. Now, how about the initial concentrations of carbon dioxide and hydrogen? Well, we didn't add any of those, so our initial concentrations are going to be 0. Now we're going to use x to represent one concentration change. I'm going to choose carbon monoxide. We're going to be losing carbon monoxide during this reaction. I can say that with confidence because I know that in order to make carbon monoxide, we need to start with carbon dioxide. But we don't have any carbon dioxide at the start. So since we're only losing carbon monoxide, I'm actually going to make our change minus x. So our equilibrium concentration of carbon monoxide will be 0.250 minus x. Now let's go on to step 3, where we use our stoichiometric ratios to solve for all the other concentrations. So let's start by looking at water. Every time we use up a mole of carbon monoxide, we also use up 1 mole of water. So if we are using up x moles of carbon monoxide, we are also going to use up x moles of water. So therefore our equilibrium concentration for water will be 0.2 minus x. Now let's look at our products. For every mole of carbon monoxide we consume, we produce 1 mole of carbon dioxide. Again, I'm getting these stoichiometric ratios directly from the balanced chemical equation. So we've used up x moles of carbon monoxide, and therefore we're going to gain x moles of carbon dioxide. So our equilibrium concentration is going to be x, which is our initial concentration of 0 plus x. Hydrogen gas works pretty much the same. For every 1 mole of CO we consume, we produce 1 mole of hydrogen gas. We've consumed x moles of carbon monoxide, therefore we're going to produce x moles of hydrogen gas, and so we'll have x moles at equilibrium. So now we have our equilibrium concentrations in terms of x, and we're going to write the expression for K in terms of x. So our equilibrium constant expression is going to have our concentrations of the products on the top and our concentrations of the reactants on the bottom. You'll notice that all the coefficients are 1, they're all raised to the first power. Now let's take our equilibrium concentrations in terms of x and plug them into that expression, and this is what we get. Now, if you look back at the original problem, you see that our equilibrium constant for this reaction is equal to 102. So we're now going to set that expression in terms of x equal to 102, and we can move on to step 5 now, where we reorganize the expression so it's in the form ax squared plus bx plus c equals 0. So the first thing we have to do is multiply through so we no longer have a fraction. And then you can see we have x squared equals 102 times 0.20 minus x times 0.250 minus x, and we need to multiply those together. So you remember how that works? You multiply the first term in each parentheses, then the outer ones in the parentheses, then the inner ones of the parentheses, and then the last ones multiplied together. So we end up with 0.05 minus 0.200x minus 0.250x plus x squared. Of course, you can simplify that and get this expression here. So let's take that and let's plug it back into the green underlined area, and this is what we get. Okay, it's still not in the form ax squared plus bx plus c equals 0, so let's keep on working through the algebra. We're going to multiply what's in the parentheses by 102 to get this expression. And now we're going to rearrange things by subtracting x squared from both sides, and what we get is 0 equals 5.1 minus 45.9x plus 101x squared. And I'm going to flip that around so it's in the form that we like, 101x squared minus 45.9x plus 5.1 equals 0. So now we're going to solve this for x. In order to do that, what we're going to use is the quadratic equation, which you may or may not remember from algebra. Basically, what the quadratic equation says is that if you have an equation with the form ax squared plus bx plus c equals 0, there will be two solutions. X equals minus b plus or minus the square root of b squared minus 4ac divided by 2a. You end up with two solutions because you have to do negative b plus the square root of b squared minus 4ac over 2a, and negative b minus b squared minus 4ac over 2a. So we're going to take this and we're going to use it to solve for x. At the top here, we see the expression that we derived a couple slides back, 101x squared minus 45.9x plus 5.1 equals 0. We have x equals 45.9, that's negative b, right? Plus or minus the square root of b squared, negative 45.9 squared minus 4ac, so 4 times a, which is 101, times c, which is 5.1, and we're dividing that all by 2a, so 2 times 101. Let's simplify that a bit. You see that we get 45.9 plus or minus the square root of 2106.8 minus 2060.4 divided by 202. You'll notice that I'm writing out all the steps because most of the time when people get these problems wrong, it's because they mess up on the math. So it's really helpful to have all the steps written out so you can go back and check to see if you went wrong somewhere. So now what we're going to do is combine what's under the square root symbol, and you can see that comes up to 45.9 plus or minus the square root of 46.4 divided by 202. Take the square root of 46.41. You have 45.9 plus or minus 6.8 divided by 202. Now at this point it's just simple arithmetic, but you can see that we're going to get two solutions. We're going to get one solution that's 45.9 plus 6.8 divided by 202, and another one that's 45.9 minus 6.8 divided by 202. So the first one, if you do the math, you end up with 0.261, and if you do the math for the subtraction for the second one, it comes up to 0.194. So now we have two possible values of x. How do we know which one is correct? In general, the best thing is to go back and look at our ICE table because usually it becomes obvious which one we need to use. So in this step, we're supposed to use the value of x in the ICE table to solve for equilibrium concentrations. Let's start by seeing what happens if you use x equals 0.261. If you look at the concentration of carbon monoxide, it's supposed to be 0.250 minus x, so if you plug in the value of 0.261 for x, you end up with a negative equilibrium concentration, negative 0.011. Well, we cannot have negative concentrations. Likewise, you could put that value in for water. 0.200 minus 0.261 will give you negative 0.061 for concentration. Again, can't have a negative concentration. So obviously that value of x does not work. And this is the way it will be with all of your solutions. You will always have two possible solutions, but only one of them will give you a concentration that actually makes sense. So let's go ahead and use the other value of x, 0.193. For carbon monoxide, we had 0.250 minus x, 0.250 minus 0.193, and you can see that we get 0.057. And then we can go ahead and put the value of x in for the other concentrations as well. Now, Again, we're going to ask ourselves, does our answer make sense? We had an equilibrium constant of 102 at 500 Kelvin, and because it's a relatively large value for the equilibrium constant, we will assume there are going to be more products than reactants, and in fact, that is what we see. Okay, now we're going to do an even harder problem. And I know it doesn't look hard at first because the reaction looks pretty simple, but it can be a bit tricky. So here's our chemical reaction. 2 molecules of iodine bromide in gaseous form going to iodine gas and bromine gas. So we have an equilibrium constant given. You'll notice this is K sub P rather than K sub C. So we're using pressures in atmospheres rather than concentrations in molarity, but it still works the same way. Our Kp value is 8.5 times 10 to the minus third at 150 C. So we're going to start this reaction by putting 0.05 atmospheres of iodine bromide in a 2-liter container, and we want to find out what the partial pressure is after equilibrium is reached. So let's start at the beginning. In step 1, we're going to make an ice table, and you can see that we have one reactant. So we have a pressure for iodine bromide that's 0.05 atmospheres. We also need to find a pressure for iodine gas in atmospheres and one for bromine gas in atmospheres, but since the problem didn't say we added any of those pressures will start at 0. Now we go into step 2, where we're going to use X to represent one concentration change. I've chosen to use X to represent the change in iodine gas, and we'll talk a little more about why we did that later. It doesn't really matter which one you choose, but sometimes your choice will be easier from an algebraic standpoint, and I'll explain why that is true here. So if we have 0 at the beginning and we add X to iodine, our equilibrium concentration of iodine will be X. So let's now go on to step 3 and use our stoichiometric ratios to solve for other concentrations in terms of X. Let's look at the other product. For every mole of iodine, we also make 1 mole of bromine. We made X moles of iodine, so we also therefore make X moles of bromine, and then our equilibrium concentration will also be X. Now let's look at the change for iodine bromide. For every mole of iodine that we make, we consume 2 moles of iodine bromide. So we're going to get fewer moles of iodine bromide over time. If we make X moles of iodine, we would therefore lose 2 moles, look at the coefficient, of iodine bromide in the process, and therefore equilibrium concentration is going to be 0.050 minus 2X. If I'd made this 1X, then our pressures of iodine and bromine gas would have been 1/2 X, and that would be pretty annoying when we want to do our math. So now we're going to write the expression for K in terms of X. First, we have to write the actual expression for Kp, and we do that exactly the way we did when we were writing the concentration-based equilibrium constant. Now again, here we're using pressures instead of concentration, so we have the pressure of I2 times the pressure of Br2 divided by the pressure of IBr squared. Remember, we have to square it because it's got a stoichiometric coefficient of 2. And then we'll take our equilibrium concentrations that we calculated in the ice table and plug those into our equilibrium constant expression. And then we can set that equal to the value for Kp that we got from the problem, 8.5 times 10 to the minus third. Now let's do our algebra and try and get this reorganized into the form ax squared plus bx plus c. The first thing is to multiply through so that we no longer have a fraction. So we're going to have x squared equals 8.5 times 10 to the minus 3 times the quantity 0.050 minus 2x quantity squared. Let's square out the expression in the brackets, multiplying first terms, outer terms, inner terms, and last terms, and this is what we get. We can combine the 2 middle terms to make it more simple, and we also are going to plug that expression now into the brackets. Now let's simplify it some more. So multiply the expression in parentheses by 8.5 times 10 to the minus third to get this messy expression, which we can simplify down to this. And go ahead and please check by math with your calculator. So now we're going to again try to consolidate all of this on one side of the equation. So we're going to subtract 0.034x squared from both sides, add 1.7 times 10 to the minus 3 x to both sides, and then subtract 2.125 times 10 to the minus fifth from both sides, and this is what we get. So here's our expression in the form ax squared plus bx plus c equals 0, and we now have it in the form where we can use the quadratic equation to solve for x. So remember again that the quadratic equation in the form ax squared plus bx plus c equals 0 has the solution minus b plus or minus the square root of b squared minus 4ac over 2a. We're going to take our numbers and plug them in here. Remember that a is 0.966, b is 1.7, times 10 to the minus third, and C is negative 2.125 times 10 to the minus fifth. Now, as you can see, this makes for a very messy expression. Let's simplify it a bit, and then let's calculate the stuff under the square root sign. So now what we have is negative 1.7 times 10 to the minus third plus or minus 9.2 times 10 to the minus third divided by 1.932. And there's our expression. So you can see that, again, we're going to have two solutions, one where we add and one where we subtract. You can see that if we add, we're going to get 3.9 times 10 to the minus third. But if you subtract, we get negative 5.6 times 10 to the minus third. Even without looking at the ice table, we have a value for x which is negative, which is not going to work at all. So we have to use that value from adding. Now, if you look at the ice table, you can see that the equilibrium pressures for both iodine gas and bromine gas will be 3.9 times 10 to the minus third, while our value for IBR will be 0.0422 atmospheres. Okay, so let's look again at our answer to see if it makes sense. We have a K value of 8.5 times 10 to the minus third, which is a very small value. When do we see small values for K? It's when we have more reactants than products. Is that what we have here? Yep, it is. So as you can see, using an ice table and following these steps helps us to figure out what concentrations of our products and reactants will be at equilibrium. So make sure you do several practice problems to get comfortable with this process, because practice makes perfect. I hope this was helpful, and I will see you again soon.